Hello, everyone. It's nice to see all of you here. It is my pleasure to introduce Paul Seifert. For today, he, as many of you know, is doing a PhD here at NTNU, and I'm very much looking forward to your presentation. Take it away.
Thank you very much. So, hello, everyone. Thanks for having me. Today, it will be about batteries, and I present the latest work, optimal trading strategies for battery storages under uncertainty. That is a joint work by Emil Kraft from KIT, Stefan Backer, and Stein Erik Fleten from this department. And yeah. So what do we have here? That's clearly symbolizing a battery. What a battery can do is it can be charged up and used later on. So it can store electricity and can basically defer electricity to a later time step. What can we do with this? Well, we can provide a lot of services. So we can engage in trading. We can provide balancing services, or we can, for example, back up renewable generation. So what we can see here is a plot of electricity prices in Germany over last year. So we have day-ahead prices in orange, intraday prices in blue. You can see they go up and down compared to the level of the intraday prices, and FCR, so fast frequency response, which is a balancing market, as a green figure. So batteries are quite efficient in what they're doing, but they're also crazily expensive. So to my surprise, I looked it up. Fraunhofer in Germany says that currently installed in this year, we have a capacity of 10.5 gigawatt hours at the power of 7.15 gigawatts, which is quite a lot. And this number is increasing quite much. So the question comes up, since we have them, they are expensive, how do we make most use of them, and how do we engage in good trading strategies for them? And we've identified that there's quite a literature gap, and that's why we started this work, and we want to tackle this. So I give a quick introduction and then tell something about the background and the model we've developed and some tentative results, preliminary, unfortunately not finished yet, but might be in the next couple of weeks. So what is it what we want to do? We want to develop a flexible, scalable solution for battery storage operators problem, and show the potential of them when we coordinate the different markets you've just seen. Yeah, and also want to see how maybe a value over coordination over time influences the problem of the battery storage. And we apply this to a little case study we have prepared based on German electricity prices, and show you some insights. So what's the problem we are facing? So we want to engage in sequential biddings, sequential bidding into the different markets. We've picked the fast frequency containment reserve, the day ahead, and the intraday prices. They follow different scheduling patterns. So they have different auction closing times, clearing times, and then in the end, it's all executed in the real time, or coming together in the real time. So we have to make decisions about the capacity we want to allocate to the markets, and are constrained obviously by the storage of the battery itself, but also the filling level. So what we want to sell needs to be filled at some point, and vice versa. The objective of our work is to maximize revenues by the operator. So far, so simple. So why is that somehow complex? So at every discrete point in time, which I call stage here, we need an action. So we need to either charge, do nothing, or discharge. So far, so simple, but it's a bit more complicated than this, because if we charge or discharge, then at what quantity are we going to do this, what is the price we're willing to pay or get, and which markets do we choose. So we have the option of 3 now. And even worse, we need then to have in all these times kind of forecasts to get a gain there. Otherwise, we're just randomly putting bits, and that's not what we want. We want to make profits. Then we have a lot of timing issues with the offset between the time we bid, then the time it takes until this market is cleared. That differs throughout markets. And also we have an offset then from the clearing until when it's actually executed. For example, day ahead, as the name suggests, it needs to be done 1 day ahead. And then what makes it complicated for the battery itself is we have time coupling constraints. So the end of the storage in one stage is the beginning, is filling the storage level in the next time. And we have also stage-wise dependencies between prices, but I will come back to this later. And on top of that, at the time of bidding for day ahead and FCR markets, we have multivariate bids, because we need to bid actually for the whole next day. And yeah, that brings some problems on itself. And the stage-wise dependency from a programming standpoint is complicated because it enters the objective function, and that needs kind of some careful considerations there. Let's have a look at the electricity prices again. So this is kind of wild what we see here. First of all, the price level is extremely high. We have here the price in euros per megawatt hour. And also the variations are just crazy. So if we compare this to the year before, we see, okay, it started building up and getting worse here. And before that, we had a completely different regime, a lot lower prices, a lot less variations. So training or working with these time series is complicated, because for a lot of solution methods, something with a neural network or machine learning, you could either train them on a lot of old data that looked completely different, or we're starting to work with that, which might change again. Currently, it's going more in the direction of so-called normal before. But if we start observing data here and we want one of these solution methods to work, and then good luck, we're waiting the next 20 years, and then it's 2040, and energy transition is already over. So we need to have something that can be adjusted to rapid macroeconomic changes, and can be, yeah, can work even in these regime changes once they occur. So to our model, we start with a discretization of this. So we go multi-stage, of course. We started planning with a planning horizon of 3 days, separate a day into 6-hour intervals. This gives an 18 stages model, and the price models for the different markets, based on something I will explain later. We discretize them into 4 discrete scenarios for the day ahead, 5 discrete scenarios for the day ahead, sorry, 4 for the FCR market, and another 3 for the intraday market. So if we put this into our modeling framework, then we see, wow, that's getting quite huge. We have then 10,081 nodes, 75 state variables. That's fine. And the number of scenarios, well, it's printing out here 13 trillion scenarios. That's likely a bit overestimated by the way we implemented multivariate biddings for the day ahead and the FCR markets, but still the problem becomes huge. So I cannot claim that it's unsolvable, because I haven't tried, so I don't know. but it becomes apparent for the solution of this, you need to be somehow smart and work with some kind of approximations. And that's why we decided to give Stochastic Dual Dynamic Programming, short SDDP, a try and apply this as a solution method to our huge scenario tree. SDDP works by sampling forwards throughout the scenario tree and then going backwards without having to visit all branches, and therefore scales a lot better than other methods there. It can also calculate a true upper bound to the optimization problem, and which is helpful to see when we reach convergence or not. Some of you in the room already have a lesson, or have today or the week a lesson. They probably know what I mean. But yeah, it's an approximation framework, and on top of that, we want to have a mechanism to adjust to the current market conditions to kind of balance out these huge fluctuation and change of market regime we saw on the last year. So how do we do this? We first start by looking at the historic price curves we have, and then we separate these curves into something we call here deterministic components, which is not entirely correct because it's not deterministic, but it's rather easy to forecast if you assume that a battery operator has access to commercial forecasts for a gas price, carbon price, and residual demand, which is a combination of the typically demand, which is relatively easy to forecast, as well as renewable generation. So once you have this, we apply a simple ordinary least square model on top of it and separate it in something that we can easily predict by this very simple model, which we now call deterministic forecast, and everything that's left. The residuals from this model are for us now stochastic, and we apply a framework of discretizing these into scenarios by doing a multivariate k-means clustering. Based on that, we get five, as I already said, five scenarios for the day ahead, 4 for the FCR. And on these residuals now to these stochastic components, based to the original intraday curve, we apply a fitting there, fit the curve over it, and take the mean and some quantiles on the right and the left and define those 3 scenarios for the intraday. Going up in price compared to the day ahead market, staying kind of similar, and having a lower price than the FCR, than the day ahead, which basically deals with forecast errors for renewables in practice. Okay, we have this. Can pick then can pick a date and combine again the forecasts we have for our so-called deterministic component with stochastic scenarios and have something to work with. Yeah, that's the stochastic clustering. Just to show you an example how this looks like. There's not too much going on. So for each day, we have, that's the FCR market. So we have 4 scenarios, multivariate curve, separating realizations from the time series there, calculating the mean gives the red curve, which we then take as a scenario. Same for the day ahead, a lot more flat in the curves. That is because we can capture in the day ahead market by our OLS model a lot more of the variations than we can do in the FCR. That is more stochastic in such a sense. Then we can look which parts of the historic time series are in which cluster, and by that, going through the year, we can calculate transition probabilities over time when a cluster is changed, and that defines then later on in the stochastic program the transition probabilities. So now going back from the stochastic scenario tree to control theory. What we have here is a node. A node is a discrete point in time at which we can take a decision. We have an incoming state that is defined by previous actions and also various factors we want to use in that node. And in that node, we are doing a transition that defines how the outgoing state is looking. And this decision is resulting then in a decision rule and introduces in the objective function a reward. So if we scale that up, we have one addition we use, and that is called in the paper a Markovian policy graph. So that's an extension to the standard SDDP, where we can have in each stage, so that's on the x-axis we have time, we're moving forward, but at each stage in time we can have different states. And with that layer on top of the standard SDDP, we can model stage-wise dependency of prices. And that's what we have. Our intraday price, for example, is dependent on the realization of the day-ahead price. We have stage dependency that we can do with this framework. It's relatively new, as I said, named Markovian policy graph by Oscar Dawson. And the states transitions we can calculate. First of all, we can see the mechanics here of the markets. So our problem is three-dimensional. I cannot print three dimensions, but I can or have here 2 dimensions, and that is the day ahead and the intraday. So here you see the market change or the market clearing of the day ahead market. There you can completely change regime, whereas transitions in between, when there's no market clearing of the day ahead, but there are clearings and movements of the intraday, you can clearly see you can change regimes here, the different states, and at the day ahead clearing you can have state changes for the day ahead, but also the intraday at the same time. And this chained together throughout our stages and also the other market gives our movement throughout the web of, or the tree of stochastic scenarios. So now on top of this, we're training for an optimal policy with some planning period, and get then a reward, which is a financial gain for the battery operator. So how does this look? So these graphs are borrowed from our upcoming Rolling Horizon program. So we have here on the left side the price realizations in 1 week. We picked just the 5th of July last year. Pretty random pick, so there's nothing here, but all you can see here is that you have the curves for the intraday, orange is the intraday, blue the day ahead. Here are the FCR prices. That's how it in reality looked. If we discretize it and imply our scenarios, we have here the day ahead. It's pretty much within our scenarios, so it's following the real prices. We have variations by the intraday. That's also within the bounds, pretty nice. And same goes for the FCR market. So it seems to kind of work what we just combined there. And that's all this should show. So what about results? Back to the case study. So we have chosen arbitrarily 10 megawatt power and 10 megawatt hour capacity battery. It's located somewhere in Germany. Where exactly doesn't really matter. And we have a 3-day planning horizons. And for this example, now picked a week, picked 3 days, 3-day planning horizon. that one here was 6 days. That's for the rolling horizon. So it's, our planning period is a lot shorter now. Yeah, apply this and let's see what happens. So first of all, here we see the storage of the battery. It kind of seems to work. I don't want to hide that here we do have some very slight yellow lines that you cannot see on the beamer, but which are deviating and violating our capacity constraint. But overall, if we have a look at the 595 quantile, it's staying within the bounds, it's trading, it's going up and down. Here it's pretty flat. That is caused by the policy choosing to go into the FCR market only. So how we modeled this is that if you bid capacity into the FCR market, you have to reserve at the same amount. So if you bid 5 megawatts into the capacity market, we don't know whether it's activated in a positive or negative direction. So we reserve both, blocking, so to say, the storage completely. Seems to be very beneficial here. That's why the model is choosing that. Otherwise, it's engaging again in trading, which it should. And here we look at the iterations and the convergence over time. We have here the upper bound. It's going down to to the real upper bounds, and here we have simulations, and they are kind of converging, which is nice. And also they are converging at the positive revenue, means yay, it works, we're making money. Tracking a bit of the storage violation, the model seems to learn quite quickly to avoid violations of storage, because storage violations are going down. Here we have the storage violation rate, how often it happens. That's interestingly not going down really, but these violations are getting smaller and smaller until they are barely there anymore. So at 16% of the times it goes into a violation, but it's less than 1%, so it's some digits behind the comma, so we don't really care about it. It seems to work. Yeah, what we also see is that the policy engages in arbitrage trading between the intraday and day ahead, which is nice, which the battery can do once the day ahead markets are cleared, and we see that there is a price deviation with a battery. We can exploit it and make money on it, and that's exactly how it should be. Now we come to the coordination. Well, it works, but it's kind of a bit unexpected, I would say. So here we have all the signal markets optimized by themselves, and from speaking from the data, what you can see is that the total revenue. Okay, first of all, let's with something positive. So if we combine intraday and day ahead trading, these are the numbers here, and here's the coordination. We see a gain from coordination. So it's about 11.6% higher. So kind of works. What the surprise is that participating in the FCR market gives such high revenues. It actually serves as a higher cap. So putting all the capacity in the FCR markets gives the highest revenue. And once we deviate from that by introducing another market, our revenues are lower because it cannot engage in the best anymore. But it's still in sample. So, but then, yeah, exactly. The question would be, why on earth do we have a coordination and not get the upper bound here? And we're kind of investigating this. One explanation would be we are not iterating till the end, so we have a end condition, and that basically looks on to a point after some iterations, if the upper bound is not getting better than a certain threshold, it kind of stops. Whereas this is not complex at all, so we can iterate till the end. And it might, so we are getting close. So here, for example, the full coordination between all markets, it's 1.8% off compared to the FCR market only. So we're getting kind of close, but we're not reaching the optimal point. And we did a lot of tries here, and it seems to get closer once you continue iterations. But that might be a shortcoming of the choice of SDDP. Once you're dependent on one very specific scenario realizations, you might not get this in the sampling, or you might have to wait even a lot longer than with other methods. And in our case, we get close, but we're not reaching it. So that might be the reason. Yeah.
The true optimal value should be higher, or at least
the true optimal value is still above this, so we haven't converged there, but we're getting close. That's what we can say. But nevertheless, it's a bit disappointing that the true optimal is just going all in for FCR. And we will apply this to, probably we will test another dates, and no, not yet, Emil. Yeah, we will investigate this any further and see. But we're testing really just a part of the scenario tree, and here we are not reaching the optimum. What are the limitations of our approach? So first of all, we have a price taker assumption in all markets that requires that the markets are sufficiently large and liquid, and so that we don't have any influence, which should be fine given our battery size, which is not substantially high. Storage losses we excluded. We originally had them in, but had in the end so many problems with convergency that we, for this point, excluded them, which is not nice. If someone in the audience has a good idea on how to fix that, I'm very happy to hear it. We haven't succeeded yet. Either extended a lot the solving time, or had some other negative influences on the allocation. Then the next big thing is we don't consider the activation risk in the FCR market, so we reserve the capacity, but assume that at the end of the period that capacity is basically unchanged, so that we can engage in up and downs in between, but they have to equal out within the 6-hour period. And then the choice of time interval of 6 hours might underestimate, or is probably underestimating, the storage potential, especially in the higher resolution markets of intraday and possibly also day ahead. Yeah. 6 stages, 4 hours. I said this wrong. Yeah, it's 6 stages over the day and 4 hours for such a period. What are the next steps? So we're currently working on a rolling horizon implementations to assess the value of coordination over time, and to have just a longer planning period. And we intend to do this with a 2-day and a 3-day foresight. And then it goes to out of sample verifications, which, yeah, is interesting to see then how this approach is performing out of sample. Preliminary conclusion.
If you wrap up in a minute, we'll have time for questions.
That's the end. We have a beneficial trading policy trained that works with the SDDP framework. We knew this from before. There are not many papers, but they exist. But what we have shown here is that you can add stages and another market and implement this as well. Also, we have what comes out as a side effect, kind of price pattern, price models for the different markets, which are tuned to the year 2020. We find a small but significant coordination benefit for the spot markets between intraday and day ahead. Unfortunately for us, but interesting insight is that the frequency containment reserve, that's wrongly written here, generates the highest revenue, and we think that the more investigations are necessary, which we are doing, which potentially others in this room can do as well. And yeah, that's it for me. Thank you.
Thank you.